I'm presenting the result of our research on design and development of interactive systems for integration of comparative visual analytics in design workflow. My name is Mariam and I'm a graduate student in the School of Interactive Arts and Technology at Simon Fraser University. In architectural design, considering design performance has become instrumental in generating and selecting design alternatives. However, current computational design tools have limitations in supporting simultaneous form exploration and real-time performance analysis, particularly when working with multiple non-parametric design alternatives. We argue that we can address these limitations through our design analytics approach by supporting seamless workflow in moving between form finding and performance analysis in design, revealing the performance and form aspects of each alternative as they are created in real time, and integrating interactive data visualizations into the design process to gain insight into the design space and to compare alternatives. We introduced DCAT as an interactive flexible prototype system adapting our proposed approach. Based on this design analytics approach, we are experimenting with design and development of interactive systems called DFlow UI and its extension DCAT, which are integrated with existing CAD applications like Rhino 3D. DFlow UI, which we presented previously, aims to simplify the creation and real-time evaluation of non-parametric design forms supported by interactive design data visualizations. Design Comparative Analytics Tool or DCAT as an extension of DFlow UI is a system solution to facilitate the evaluation and comparison of non-parametric alternative design solutions. In this research, we adapted the design study approach as a problem-driven research method. It involves analysis of a specific real-world problem faced by domain experts designing a visualization system that supports solving this problem, validating the design and reflecting about lessons learned in order to refine visualization design guidelines. We developed and used DFlow UI and DCAT prototypes to generate knowledge about how design alternatives can be compared with each other using their associated form and performance data as an integral part of design exploration using interactive design analytics visualizations. Our methods are literature review, tool analysis, expert review, and prototype design. The outcome of this study includes a set of high-level requirements, several user interfaces experimented in real-world practice, and a tool ecosystem and architecture schema unique to design data analysis. Accordingly, we propose four initial high-level requirements for DCAT. A design comparative analytics tool supports the comparison of design options by visualizing both form and performance data in real time or on demand and in the same context they are created. It also enables customizing visualization of concerns such as including or excluding data, selecting visualizations, toggling performance parameters on or off to compare ordering design options, and so on. The system allows exploration in the modeling tool while keeping visualization on the locus of attention. And finally, it provides support for storing, retrieving, and sharing multi-state design form and data in the modeling systems. To address these high-level system requirements, we designed DCAT interface to facilitate diverse comparison tasks such as juxtaposed visualization of forms, selective comparison of performance metrics, grouped by alternatives or grouped by performance metrics comparisons, and so on. All of these comparison tasks can be performed in real time or on demand. The tool is flexible to include diverse performance metrics such as total floor area, net solar gain, view quality, cost per program, and so on. The interface consists of four main interaction panels: alternatives and performance data selection, interactive 3D geometry visualization, performance metrics tabular view, and performance data visualizations. The Alternatives and Performance Data panel provides customizable visualization of design data following the selection of design options. The system can export the comparison data to be shared with others or be further analyzed in design navigation tools such as Design Explorer, Design Sense, and DArt in a parallel process. Juxtaposed design models are presented in the 3D visualization panel. We use the color-coded 3D form view to indicate the associated functions of the building blocks. The tabular data view provides an overview of the selected performance metrics in a list with selectable data items. The bottom panel on the interface is composed of customizable visualizations such as bar charts, parallel coordinates plots, and line charts to facilitate visual comparison of design alternatives. And finally, the tool is configurable to enable exploration and analysis of different aspects of the design based on the project at hand. The interface itself is compatible with larger screens as well as smaller screens. So here you can see the system architecture of Flow UI, which is built on 3 functional modules: design modeling, data extraction, and design performance analytics. The design exploration task workflow starts with creating design models as non-parametric geometries by using directly interactive CAD tool like Rhino. The modeling setup directly links geometries to the data extraction module, which recognizes the functions and program requirements associated with the geometries. On the interface in the Design Analytics module, designers can select the relevant data for the task at hand to be computed and visually displayed. These visualizations assist designers to investigate each alternative and compare multiple alternatives as they are changing in the design modeling environment. To conclude, this research project mainly argues a mismatch between the tasks and tools for working with multiple design alternatives, especially for comparison tasks considering alternatives, forms, and performance data. This mismatch creates a significant bottleneck in the design workflow. Hence, we should focus on searching for a new set of tools, especially designed to augment designers' capabilities for exploring multiple alternatives informed by data as early as possible in the design workflow. Current version of DCAD will be improved by increasing the computation speed, better integration of systems' fragmented modules within the workflow, reducing manual interventions for initial setup of CAD environment, and testing the reliability of plugins we use for development of DCAD. DCAD cannot change design models in its current implementation. The information flow is unidirectional due to the technical difficulties we have faced in the system's API, which we will address in the next phases. Moreover, we have identified the high-level requirements for DCAD system. The validation of these requirements will need further testing of DCAD visualizations with designers working on real-world cases. In the next phase, we will conduct an expert review as a formative evaluation of DCAD with respect to predefined criteria on both the task and the visualizations supporting these tasks. This review is expected to reveal the concerns to be addressed in the next iteration of DCAD system. We also plan to test the functional features of DCAD in practice in collaboration with our industry partners. This research was supported by Simon Fraser University and MyTax Accelerate Program of Canada in partnership with the Boeing Company and Stantec Vancouver. And here is the list of references we use in this paper.